I can start from here. Okay. Thank you. Yeah, so this is an ongoing work. Joint with RC. Venugopal. Okay. So let me first set up the problem. So let's start with a primitive new form of weight K, label N and character epsilon as usual. So K is some integer bigger than equal to 2. Yeah, and to begin with, let us assume that P is a prime of good reduction, that is P is co-prime to the level N. And attached to this primitive new form, we have Galois representation. Global Galois representations. We are considering periodic one. Okay? So, two-dimensional over some finite extension of QP. And further, we want to restrict our representation to the local decomposition group at P. So here also we have periodic base field and we are restricting to. So this is the local Galois representation we are interested in. And here we can always choose a Galois stable lattice. And then go modulo the maximal ideal. Let's call it ME inside the ring of integers of E, right? So this we can do, and this gives us a mod P representation. Let's call it rho F bar. So GP is GP. I have used this notation here, is the isomorphic to the Galois group of QP bar over QP. So rho F bar restricted to GP is of course a representation of GQP to GL2 of the residue field of E, right? Or we can embed it inside GL2 of FP bar. So the broadly the question we are interested in is that what is rho F restricted to GQP bar? What is the shape of it? So how does it look like? Right. So now let us state some facts about this. So already I have said P is prime of good reduction. So then again we can assume that the character takes value 1 at P. So this we can do by twisting if necessary. twisting Okay, so after assuming this, we have two possibilities for this local mod P Galois representation. One is if P is ordinary. So if, okay, so let me also introduce this notation that I will use. So let V be the valuation from QP bar to Q union infinity normalized by valuation of P is 1. Okay. So now if we continue from there, so there are two possibilities. One is the ordinary case. That is when the valuation of the pth Fourier coefficient of f is 0. In that case, we know that rho f bar is isomorphic to. I will just define the notations in a moment. Mu AP direct sum omega to the k minus 1 mu AP times omega plus mu AP bar inverse. So it is reducible clearly. And if the valuation is positive, then we know that this is irreducible. So here I am talking about the local representation. You have to remember that from now onwards, everything is local at P. So rho f bar is irreducible. Yeah, so yeah, that is a good point. So when we do choose a lattice and go mod the maximal ideal, it is defined, this reduction is defined only up to semi-simplifications. Well defined. Why? Because you are choosing a lattice, and for different choice of lattice, you may have different reductions. So, by my definition, rho f bar is a representation of GQP and is a semi-simple representation of GQP. Okay. So in this case, this is irreducible and it is isomorphic to a crystalline representation that is defined, denoted by symbol, and this object is defined using periodic Hodge theory. I will not write down the definition here, but it's a irreducible representation of Hodge-Tate weights 0 and k minus 1 and slope equals to the valuation of AP. So basically, this what it says is we don't know much about how this, sorry, here there is no bar. Yeah, so this is nothing is, so far nothing is known about this rho f bar. I mean, things are known, I will say that in a moment. But rho f itself is a complicated object when the prime P is non-ordinary. We know that it is irreducible, that's all we know. And it is corresponds to some periodic Hodge theory object, some filtered phi module. And it is characterized by these two quantities, weight K and the periodic coefficient, pth Fourier coefficient AP. Right, so this is known. And then And these are all possible irreducible, all possible crystalline representations up to twists by characters. So now we modify our question a bit, generalized question. How does BKAP bar look like for different K and AP? So as K and AP varies. Okay. So this is all about generality. Now let us, I will say some what is known in the literature, and before going into that, let us see what are the answers that we do expect. I mean, what should these representations look like? So let me state this classification theorem. So let rho bar be a continuous representation from GQP to GL2 of FP bar. Then there are two possibilities. Either it is irreducible, and in the irreducible case, it is isomorphic to induction omega 2 to the power A for some integer A such that P plus 1 does not divide A. So this is the irreducible case. Or it is whenever it is reducible, it is of the form omega A direct sum omega B, and this is reducible, of course, and this is true up to twist by some character up to. So any representation will be twist of these representations by some crystalline character. Some continuous character, yeah. So what are these omega 2, omega, etc.? I have not defined. I have not also defined this mu thing. So these are omega 2 is some character on the inertia group. It takes value in Fp square star, and this is Sayre's fundamental character of level 2. Omega is also similar character. It is Sayre's fundamental character of level 1, and omega equals omega 2 to the power P plus 1. And yeah, and when I am writing mu lambda, this is unramified character sending geometric Frobenius to lambda. And what do I mean by, sorry? No, so I will tell you. So, okay, so I have not yet defined what is this ind means. So this ind, this is the unique irreducible representation of GQP such that determinants is omega to the power a, and restricted to inertia, it is direct sum of two characters, omega 2 to the power a and its conjugate. Okay, so this is, if we call this rho bar, so there is a unique irreducible representation satisfying these two properties, and that is what this is. So why we are writing end here is that it is actually induction of something from Galois group of the quadratic unramified extension of QP to GQP. And we have a omega 2 power also here. And we may have some extra character. It is not, this character actually depends on some choices. So we don't mention it that directly it is induction. We are saying that it is induction of some character, but it is defined by these two properties. Okay, so these are the two possible shapes that we can expect. So since A and B, there are not infinite choices. These are finite order characters. So of course, there are finitely many choices for A and B, and also for A, there is finitely many choices. So it's a very, like, one knows what to expect in the mod P scenario. But though in the characteristic 0, things are a bit complicated, one knows what to expect in mod P scenario. So one asks this question, so what will be the reduction given if we give you K and AP, can you decide what would be the reduction of the representation? So this is, and this theorem, maybe I should mention a couple of things about this. So this theorem is followed from the fact that while inertia is a normal subgroup, so any irreducible representation, the wild inertia should act trivially. So therefore, you should, when you restrict to inertia, you must break into two characters because your tame inertia is time to P. And so the lot of this mod P theory is playing a role in proving this theorem. Basically, what is the important thing is that any P group has a fixed point necessarily. So that is the key to all this. So this happens in PP case, and then therefore, okay, so this is the answers we expect. So now I will state some results that whatever is known to me and whatever is available in the literature. So I will list some of them. So first, this kind of reductions were computed in this range. First, up to P plus 1, it was due to Fontaine and Edixhoven. And then after that, up to 2P plus 1 due to some computation by Breuil. Yeah. So for small weights, the result is very explicitly known when it is irreducible, when it is reducible, and what is the exact A, B, etc. in those cases. Everything is known. Yeah. Sorry, here I think I should write mu lambda 1 and mu lambda 2. Yeah, so it should not be twisted by the same unramified character in both places. So I have to include that separately. Okay, so yeah, this is one thing that is known. And then another kind of result is known when the slope is very big compared to K. So when slope, so this we call this slope, valuation of AP is bigger than the most recent improved bound is this K minus 1 by P, floor of that. then the answer is known by the work. So there was essentially some bound by Bajeli-Zhu and recent improvement by Bagdal-Levin. So this is one thing. And the other family of examples where it is explicitly known is when slope is small. So slope is up to 2, say 0 to 2. And this is due to buzzard G, Ghate, myself, Rosenstein, Rai, and some more names to be added soon maybe. Yeah, so these small slopes also, the results are explicitly known. I am not going into the details of the results because what I will do is I will concentrate on the case P equals to 2 now, and I will see how these similar methods works for P equals to 2. And none of these results are, so this is strictly for P odd. All these results are for P odd. Some of them are even for some technicality, we have to assume P bigger than 3 or 5, but essentially definitely for P odd. I have not really thought about P equals to 2 case so far. Yeah. So another thing I want to mention here is the complexity at the exceptional weights. So we have noticed while doing this and while if you read any of these papers results, you will see there is some observe that at half integral slopes, and if K is congruent to 2V plus 2 mod P minus 1, in this special congruence class, the behavior of VK AP bar is like uncannily complex, very complex. And there is, okay, so I'll go. There is Ghate's conjecture called zigzag conjecture, which gives a general pattern, predicts a general pattern of what will happen in these cases. But in particular, you can check at V equals to half, 1 or 3 half, which are completely calculated. There you can check that the complexity you can already see. So generalizing all those. So what is zigzag conjecture predicts the behavior of VK AP bar, at least restricted to inertia, at these exceptional weights. And also recently has announced a proof of this exact conjecture at some special points which are close to semi-stable points. But yeah, we are not going into that deep now. So now I am mentioning all this because after I state my result, I would like to make one or two comparisons, how the case is different for p equals to 2 and this kind of things. But let us now concentrate a bit on p equals to 2. First of all, what is the possibilities? Here our theorem is also till here. So then you know that the fundamental character is actually trivial when we are working mod 2. So therefore, if you are reducible, your representation has to be unramified. And if you are irreducible, then you are isomorphic to induction of omega 2. That is the only case. So there is only one irreducible possibility, and up to unramified characters restricted to inertia, only one reducible possibility. So in this case, the question reduces to is Bk AP, let's write A2 here, Bk A2 bar irreducible, or when is it irreducible and when is it reducible, things like that. And if we have reducible, then we also need to worry about these constants lambda 1 and lambda 2. Yeah. Okay. So maybe I will state our theorem here. So we are like looking for a yes, no kind of answer now. So our statement is as follows. Is 2, let's assume k is bigger than equal to 5. And let's say let t denote the valuation of r minus 1, where r is, this is somewhat lots of time used in the literature, r is k minus 2. And let's define a new quantity tau to be the valuation of a2 square 1 minus 2r by a2 square. Okay. So with this, what we can say is then Bk A2 bar is irreducible if first of all, if k is even. Second, if k is odd, and sorry. I have made a very big claim here. So let me just underline another big assumption. So small slope. So assume the slope is between 0 and 1. Then we have Bk A2 bar is irreducible if, maybe I will go to that board, write everything properly. So if first of all k is even, then if k is odd and the slope is not half. Next, suppose k is odd, the slope is half, but tau is not equal to t. Okay, so I have defined two quantities here. Okay, r I have defined, but t I have not defined. So t is by definition the valuation of r minus r. Okay, so if tau is not equal to the valuation of r minus r, still you are okay. And then suppose k is odd and slope is half and tau equals to t, and then we have an extra condition here, equals the valuation of 1 minus 2r square by a2 square. So in this case also we could manage to prove that the answer is irreducible. And yeah, so far this is a work in progress. So far we have this much only. And yeah, this completes the statement of the theorem. Now let's have some comments and comparisons. So I forgot to mention before stating my theorem, I should have said what is known for p equals to 2. Very little, but some things are known. So already known for p equals to 2 is when k is between 2 and 4, then the answer is irreducible. This is known, and we know that if I have that, yeah, I also have the second point there, the result for p odd. So actually first 2 points there are even applicable for p even. Only the third point is strictly for p odd. So we have, if valuation is bigger than k minus 1 by 2 and floor of that, then the answer is, if you analyze the result of Basel-Lizu and Bardoll-Levin, you get the answer is irreducible if k is congruent to 0 or 2 mod p, and reducible if k is congruent to 1 mod 3. Okay, so these are the two kinds of result I could find in the literature about p equals to 2. So therefore, the smallest possible weight where I couldn't find any answer is k equals to 5 and slope lying between 0 and 2 included. So this is unknown. Okay, so we have started from k bigger than or equal to 5, that is, so there is no overlap with this first case here. So now what I will do is I will state some known results for p big odd primes and see how it is different in this case, but not so different. Yeah, I'm coming to that. Yeah, I think there is example. Yeah. Yeah, one can think the way the statement is given, one can think that possibility is always irreducible. And let us start with that comment itself. At slope half, the reduction can be reducible. So we have numerical example. For example, let's take a equals to 5 and a2 is √2. Very simple. So then this is irreducible. So this is numerically checked. Using Sandra's algorithm. Okay, and we can also see what is tau and t in this case. So tau is valuation of 1 minus 2r by a2 square, right? So 2 times 3 by 2. So this is valuation of minus 2, which is 1, which is the same as valuation of r minus 1, which is 2. Okay, so tau equals 2. And further, if you check the valuation of this second quantity, let's call it tau prime, you will see that tau prime is bigger than tau in this case, equal to 2. So actually, this example lies outside our hypothesis, and it is indeed reducible. Okay, so we are still just, we know there are reducible cases, but we just could not catch it yet. So that is why it is a incomplete result. Okay. Yeah, so now I will recall some results that is known for odd p, as I said. So for example, what happened at slope half? I'm just trying to see this, whatever is happening here at point 3 and 4, how is that comparable to other known cases? So let's recall. So slope half. So which is comparable with this, right? So exactly slope between 0 and 1. Slope half, and this is result by Buzzard and G. 2013. Here they have, if you look at their result and their criterion and somehow try to write down their expression little bit like our expression here, what you will find is that V bar K AP for P odd is reducible if and only if, I think, just be sure. Yeah. Tau is bigger than equal to t plus half. where t is same as ours, but tau definition is valuation of 1 minus PR by AP square. Instead of 2R, we had, if you replace that with PR, and their theorem is not exactly stated in this form, but this is, if you just do a little bit playing around with this formula, you get this is what the answer, their classification is. So it is reducible if and only if this happens, and they also explicitly gives what the structure is, which is important when P is large, P is odd. Okay, so this is one thing, but here we are noticing that after certain points, if tau is less than t plus half, we have irreducible answer, but if tau is big enough, then we always have reducible answer. But in our case, what we are having is we are having like an isolated case at tau equals to t. Tau bigger than t also is possible, then we have irreducible. Tau less than t is also possible, we have a reducible answer. But it's like somehow sitting in between, the reducible cases are sitting in between these two cases, which reminds me of the slope 1 case actually, slope 1 and P odd. So this is result by Ghate, myself and Rosenstein. So there I want to go into the exact formula, but what we get is something very similar. V bar AAP is irreducible if tau less than t, reducible if tau equal to t, and irreducible again if tau is bigger than t. And of course, these two irreducibles are different in that case. And this happened when if, oh, sorry, very sorry, all of this happening at the exceptional point. So here in the hypothesis also we have K is congruent to 3 mod P minus 1. Okay, so K is 2V plus 2 mod P minus 1. Only then reducible case can occur. Okay, so here actually K is congruent to 4 mod P minus 1. Then we have this kind of trichotomy, which is kind of similar to what we are getting in this case. So apart from these comparisons, I don't have much to compare. So the thing is that both these slope half and slope 3/2, both these are, so comment, both of the above examples are again special cases of zigzag conjecture. Where he gives a nice criterion and also he gives a formula for tau. So here also tau, yeah, this tau is different from that tau, but some similar formula. Tau is something like AP by P minus P by AP. I choose 2. Valuation of that. Okay, so there is some formula for in general for some tau. And depending on which range tau is lying in, t to t plus half to t plus 1, etc., the representation varies from irreducible, reducible, irreducible, reducible, like that. So that is a general format is there. You can look up. But for p equals to, so this is also for p bigger than 3, bigger than equal to 3. And for p equals to 2, I don't know anything. Yeah, so something like that. And this is somewhat explained by the work of Ghate, Chitrao and Yasuda. Which says that somehow at this point, this bizarre complexity is happening because these points are somehow close to semi-stable points. Okay, so in some space of triangle in representations, these points are close to semi-stable representations. So we can see that for semi-stable cases, AP square is P to the K minus 2. So K can be 2V plus 2 in particular, right? So that is where the complexity lies somehow. So some reason to explanation using shouldn't really say explanation, but yeah, so somehow the complexity, the root of the complexity is probably that these points can lead to some semi-stable point where the representation is more complex, and L invariant is involved, and so it's not expected to be so simple. Okay, so now, yeah, so this is all I think I wanted to comment about the result. Now I can make some comments about the proof. So proof uses mod P Langlands, mod 2 and 2AD Langlands program and the compatibility between that. So basically what happens is to compute VK A2 bar enough to compute the reduction of some automorphic object. So this thing where this pi k A2 is defined to be the induction of compact induction of kz to g of sim r is the same k minus 2 sim r qp bar square quotiented by the image of t minus ap. So t is the Hecke operator. And we have this representation where G is GL2 of QP, K is the maximal compact subgroup GL2 of ZP, and Z is the center. And you take this symmetric Rh symmetric power as a representation of GL2 of ZP, and then extend it to Kz by acting the scalar P trivially, and then induce it from Kz to G. So that is standard procedure. So we have this object and you choose a lattice here. So lattice is, so let theta k comma ap be the image of the integral lattice. So image of sim r ZP bar square, induction of sim or GP bar square. Inside pi KAP. And then if you can compute the reduction of this lattice, that uniquely determines your VKAP bar by mod P local Lagrange. So this is the method of Broglie. Broglie introduced it when he was proposing the local Lagrange in the same paper, and he computed the reduction using this technique for small weights. Okay, so this is the basic thing. Now what happens at P equals to 2 is, we know that this theta bar, clearly there is a surjection from induction of VR to theta bar. What is VR? VR is the mod P mod version of this symmetric power. Okay, and you can consider GL2 FP acting on it, and then inflate that action to GL2 GP, and then induce from KZ to G in the standard. Sorry? Theta, yeah, theta bar is theta bar KA. Just for saving time, I'm writing like this. So this is the idea. Now what happens is, when slope is small, 0 less than V less than 1, this is the observation of Buzzard and G. Just I have to check once more that it is valid for P equals to 2, that there are some certain submodule of VR that lies in the kernel. So certain submodule, so there exists, for time saving, let me just say some submodule WR of VR, depending on this slope, lies is there, such that if we call this map P, then the induction of WR lies in the kernel. Okay, so therefore what we have is, we have a map from the quotient, induction of the quotient to theta bar, and the thing is that in our particular case we computed that this quotient is nothing but V0, which is the trivial representation. Okay, so now we are with a map from the induction of the trivial representation to theta bar surjection, and we want to say what is there in the kernel further. Now, what is this space? This space is parameterized by space of, so this is the same as the space of finitely supported functions if 2 bar valued functions on the tree of GL2 QP. So you can think of the lattices in mod P vector space of dimension 2, and the homothetic classes of that lattice forms a tree if you, this is standard, so that on those lattices, homothetic class of the lattices, this group acts transitively. So therefore, basically this Kz mod G and stabilizer of one lattice is Kz, one central lattice is Kz. So therefore, Kz mod G is the in correspondence with the vertices of the tree. Okay, so this tree, let me draw a picture of the tree here. So for typically for any prime, every vertex has valency p plus 1. Okay, so for p equals to 2, our picture looks like this. Etc. So this space therefore is the space of, so you are assigning some value on each of these vertices, and you can only assign values to finitely many vertices. That is the space. And how does the Hecke operator T act on the space? It acts by the following formula. That you have let's say value at a point is sum of the values at its neighbors. I remember it like that. So TF of a vertex V equals sum of FW, where W has an edge with V, shares an edge with V. So if we have our function is supported on this one point, then T of that function will be supported on these 3 points. Okay. So now why do I worry about this? So finally, we have to prove that this theta bar, what this theta bar actually is. We know it is in the image of mod P Langlands. So it has to factor through some co-kernel of some Hecke operator or some variation of that. So that we know, and we are looking for exactly what it factors through. So there are 2 possibilities in this case. So possibilities for theta bar. One is, let's give a name to this map. Let's say P bar. One is P bar factors through T of image of T. Let's write like that. Image of T or co-kernel of T. So image of T comes in the denominator, or it factors through image of T square plus CT plus 1 for some C in F2 bar. Okay. And the first, if we get the first case, then your answer is irreducible. And if you get into the second case, then the answer is reducible. And also this constant C tells us what will be the unramified characters involved. Okay, so this is the basic idea. And now let me, so what happens is this T, there are 2 T's involved here. So one T is acting on this space and one T is acting on this space here. Okay. So one is acting on characteristic 0 representation and one is acting on these very simple functions on the tree. So what we typically do in this technique is look for functions in induction of nothing special about 2. So sim r qp bar square such that T minus AP of F is integral. Integral means it lies in the induction of sim r GP bar square. And then if it lands in GP bar square, you can go mod P. And then you can go through this map VR to VR mod WR. So now, so here integral and the reduction T minus AP of F bar maps to, let's say T of some function, let's call G. In G is not a good thing, so let's say phi in induction Kz to G1 such that the G span of phi is the whole representation, such that phi generates this thing over G. So since it is integral, therefore, since it is in the image of T minus AP, so it must die in theta bar. Okay. On the other hand, if you go mod P, you are saying that this is equivalent to the image of T of phi. Phi generates this whole space, therefore, T of phi generates the T image of this whole space. Thus, your representation theta bar factors through the image of T. And once you know that, you can use the Langland's correspondence to say that it has to be isomorphic to this thing. So final conclusion would be theta bar is isomorphic to induction Kz to G sim R. Sim R. So let's say 1. So this is a typical supercuspidal representation of GL2QP. And so if you find something like this, then you get the irreducible conclusion. Okay. And for reducible conclusion, you have to look at something more, because you have to look at not only the image of T, but the image of T square plus Ct plus 1, which is more complex. For how much time do I have? Time is over, right? There was any bell? Okay, sorry. Yeah, so I can stop here. The one more comment maybe I will make, that K is even, the function I use is pretty simple. And also K is odd and valuation is not half. Not so difficult, but we have to find two different functions for less than half and bigger than half. But the functions here we used have support of 4 vertices. However, the function we needed to use for slope half are not of bounded radius. So it's something like in this graph, if you imagine a disk of radius, let's say 2t or 2t plus 1, something like that, a disk of that radius. So if you consider 1 unit as one edge at 1 unit, so then our function is actually supported on a disk of that much radius. So therefore the function support is actually dependent on the valuation of r minus 1. So it's like not bounded by any fixed number. Yeah. So things are complex at valuation half, even though we are in irreducible case, the functions are a bit involved. Sorry for taking more time. Thank you.
Thank you very much for this nice talk. Are there any questions for the speaker? Maybe I can ask a couple of things. So I was curious about your condition that the slope should be between 0 and 1. There's many situations where you expect the slopes actually to be integer so that this condition doesn't arise. For instance, Buzzard has all these conjectures that when it's regular, then this kind of thing should never happen. I was wondering if anything is known about how often a slope can be non-integral.
Yeah, it is a very rare thing. So like we are not really starting from, though I started with the motivation that we are starting from a modular form, but we are just taking arbitrary Galois representations, right? So the slope is anything, but whether it really occurs as slope of a modular form, that is a question, and not much is known. Like example, if you look for, very rarely it is non-integer, and even then it is half integer most of the time.
Yeah, that's right. That was my impression also.
But there is no like theoretical reason why that should happen as far as I know. So, and I think so this kind of results can maybe also used to prove some results about slopes, that slopes cannot be non-integers or something like that. But we have not really assumed that our representation comes from a modular form.
Yeah, right. Yeah. So when it does come from a modular form, can you bound the denominator in any real sense? You said when they're not integral, they're often half integers. Then there's a couple of examples where you can get like a 3 or a 5 in the denominator. But I don't know if there's anything bigger than that.
Yeah, I don't know. I actually want to know, but I don't know how to find also these examples. Yeah.
There's nothing known.
Right. And it will be very large weights or, yeah. So, yeah, I don't know much examples of non-half integral slopes.
Maybe another very quick question, but what about the case of infinite slope? So if you have, for instance,
yeah, that is already covered, no? This by
it's always irreducible, is it?
By this, there are two. Okay, so this also I forgot to mention. So there is also a conjecture that when k is even, then your representation at non-integral slopes must be irreducible. Non-integral slopes. But that miserably fails when p is 2 because of this condition. So when k is, if you can always choose k even such that k is 1 mod 3. For example, let's say k is 4 mod 6, and you can choose slope to be large enough, then your representation have to be reducible. So yeah, it is not true for p equals to 2. However, in this range, it seems to be true between 0 and 1. K even is always irreducible.
Thank you. Any final questions?
No. So the thing is like they are not separately proved for p equals to 2, but their general Fontaine-Dick-Savens result and Breuer's result for k equals to 4. They are like proved for in general, but they included p equals to 2, did not explain. And same for this one.
Okay, if there are no further questions, let's thank Shalini again.